Okay, in this lesson we are going to learn about common logs, which are also logs that are in base 10. It's what you use on your calculator when you see the log key. Okay, so base 10 logs are also called common logs. So common that we don't even write the base. It's just sort of like assumed to be there. Okay, so like if I were to write log 2, what that really means is I'm assuming you know that that's log base 10 of 2. Okay, so I don't write that base 10. So if there's not a base written, you can assume that it will be 10. Okay, back in the day before there was calculators, there was this big binder of a table basically that gave a bunch of values of logs that were in base 10 that you used. But luckily, we don't have to use that table anymore. We can go to our T84s and the calculator will kind of do that table for us, okay? So on your calculators, if I ask you to calculate log 3, and again, what that really means is it really means log base 10 of 3. We just don't write that base 10 in there. Um, but you do have a log button on your calculator, and you can just press log 3, and you should get 4.771. We round logs to 4 decimal places always, which you're going to have to kind of get used to, but you will need to do that. So the log button is right next to the number 7. Log of 3 is 4.771 when I round that to the 4th decimal place. Okay? So just a little lesson on your calculator there. Um, how does this help us? Well, when we have problems where we have exponents in the or variables in the exponent like we do right here, we can use logs to solve them. I cannot get 3 or 11 as the same base, and so what I need to do then is I need to use logs to solve them. If I can't get them as the same base, then what I do is I take the log of both sides. So I will take the log of 3 to the x and log of 11. And again, I just wrote log, but what you're really doing is you're taking log base 10. Okay? So you will take the log of both sides, and then you would use your little exponent rule, and you know that this x can come out in front out here, which puts me to this spot right here. And then of course I can solve for x by dividing by log 3, like that, which I showed you in the next step. And then at that point, you can just put it into your calculator. And I can take log 11 divided by log 3, and it will spit it out for you. All right, if you want to add that property to your log sheet, you are welcome. All right, and so here we go. I am trying to solve this algebraic equation. I have a variable in my exponent, and I cannot get 2 and 10 as the same base. So my solution to that problem then is to take the log of both sides. So if I take the log of both sides, that's where I'm at. Then this x that's right here, I can use my exponent rule or my power rule, and it can come out in front. So I will have x times log of 10 equals log of 2. Okay? Your x is your variable, and so to solve for that, you would want to divide by log 10. And that cancels. And at this point, I will just put this into my calculator. Log 2 divided by log 10. You have to be careful with parentheses, but here we go. Log 2, make sure you close that because I'm done taking the log of 2 now, divided by log 10. And when I type that into my calculator then, I get 0.3010. Okay, and I always like to put the little squiggly sign here because we are estimating here. So this is 0.3010. 4 decimal places when you use logs to solve, please. All right, here's one for you to try. So go ahead and hit pause, try it, and I'll put the answers up here. All right, here's another one. Again, I cannot get 3.1 and 9.42 as the same base on both sides. And when you can't get them as the same base, you will take the log of both sides. And again, log is, I'm not writing the base 10, it's just assumed to be there. But I will take my exponent and put it out in front. Okay. And now at this point, you can divide by log of 3.1 to get that a minus 3 by itself. Okay. So then I have a minus 3 equals, and I can put that mess into my calculator. So I will take log of 9.42 divided by log of 3.1. Go ahead and try it. You should end up with 1.9824. And then I can add the 3 to it. And so A becomes about 4.9824. And that is your solution to that one. All right, here's another similar one. If you want to try it, you can. If you want to fast forward, go ahead. But I will put the answers up here so that you've got them. All right, this one is also fairly similar. Again, I cannot get 6 and 2 as the same base, so I will take the log of both sides. This comes out here as an exponent, and so you have x minus 5 log of 6, and this comes out here as an exponent, so I have 7x plus 2 log 2. All right, this one is not going to come out quite as pretty, but it will work. So what I wanted to do is I want to get one of these variables isolated. So I will divide both sides by log 6. You could also divide both sides by log 2 if you wanted, but I am going to divide by log 6, and then I will have x minus 5 equals. Now, I can get a gross icky-decimal for this quantity right here. So I am going to do that, and I am going to put log 2, close your parentheses, divide by log 6 into my calculator. And when I take log 2 divided by log 6, I get it an icky-decimal, which is about 0.3869. And of course, you're going to round to 4 decimal places like always. Okay, and then what you need to do is you need to take that icky-decimal and distribute it. Okay, so 7x times that 0.3869 gives you 2.7083x, and then 2 times 0.3869 is 0.7738. All right, and then of course now you just need to solve algebraically, and so I will subtract x, and I will have negative 5 equals 1.7083x plus 0.7738, and then subtract 0.7738. Okay, and then I will have negative 5.7738 equals 1.7083x. Divide by that. So the process isn't so bad, it's just that you're dealing with icky numbers, but that's okay. You should get negative 3.3799. Whew-da. Okay, so that is how that one works. All right, and then here's one for you to try so that you can see how this works. I don't know why that one's not coming off, but it's not. But that's what you should get for your answer. All right, then we really quickly need to talk about the change in base formula. And the change in base formula just allows us to simplify this in kind of one step instead of having to write this all out. Okay, so in the past what I asked you to do, your calculator, if I had this, okay, let's say I had this. Your calculator only does logs in base 10, so I could not punch into my calculator log of 25 because I am in base 4 on this problem. So in order for you to use your calculator to help you, you need to change the base on it. Now, what we did in the past is we said, okay, this is x, and then I went 4 to the x equals 25, but I still can't take the log of, or I still can't get 4 and 25 in the same base. Now, you could solve this from here, like we just did, and take the log of both sides. And when you take the log of both sides, this exponent comes out here. So you'll have x times the log of 4 equals log of 25. And then, of course, you would divide by log of 4. That's where I get the change in base formula. Okay? So the change in base formula, instead of doing all of that algebraically, when you see something like this, the shortcut would be to use this change in base formula and just simply take the log of 25 divided by the log of 4. Okay? If you need to see it algebraically and understand why, then you can, but there you go. And you can add that change in base formula to your log sheet. And here we go. So all I need to do on this one is take log of 5 and divide it by log of 7. And when you take log of 5 divided by log of 7, you should get 0.8271. Okay? And here we go. This would just simply be log of 13 divided by log of 8. And you should get about 1.2335. So you can check that out on your calculator. And then lastly, one more. You can do log of 3.9 divided by log of 0.5, which should come out to be negative 1.9635. So that should do it.